Sir, is it visible, sir? Pardon, sir, is it visible? Sir, కనబడుతుందా ఇది?
సార్
సార్ ఇది పీపీటీ కనబడుతుందా?
ఎస్ సార్ కనపడుతుంది సార్.
Okay, sir. So, good morning, sir. Today I am going to review the syllabus once again. The foundations on expansive soils. You can see the image of expansive soil here. So, expansive soil means the soil which tends to expand when it receives water and shrinks when water is dried out. So, such type of soil is known as expansive soil. So, the expansive nature is due to presence of mount-formed and clay mineral. The expansive nature of soil causes heavy damages in structures resting on it. So the most dangerous claim is mount-mounted clay mineral. This mount-mounted clay mineral causes the swelling and shrinkage behavior of the soil mass. So these soils are very hard and dry state and possess high shear strength. These properties are reduced when it receives water. So in summer month, it is very common to see shrinkage cracks with hexagonal column structures. So vertical cracks extend up to a depth of 3 meters or with 10 meters width. The distribution of expansive soil in world. So in world, the expansions are distributed in various countries like Africa, Australia, India, South Africa, USA, Israel, Indonesia, Burma, and other countries in Europe. Distribution of expansions are in India. So in India also expansions are available in Madhya Pradesh, parts of Rajasthan, Uttar Pradesh, Karnataka, etc. So 20% of total area of India is covered with expansive soil. Expansive soil in India. So in India, generally expansions are called as black cotton soil because these soils favors the growth of cotton. That means they also most of the black cotton soils are in black in color. That's why it is called as black cotton soil. So black cotton soil because of that color and prosperity of growing cotton, it is called as black cotton soil. So in India, the black cotton soil have the following properties. So liquid limit is in the range of 50 to 100. Plastic limit is in the range of 20 to 65. Shrinkage limit is in the range of 19 to 9 to 14%. The collateral content is less than 2 microns and the range is 40 to 75%. Damages caused by expansive soils are the damages to roads, damage to canals, damage to water pipes, sewer lines, heaving and cracking of road slabs, vertical, horizontal, and diagonal cracks in buildings. Walls are pushed outwards, tilting of structures. So you can see here the damages created by expansive soil on pavements. So damages created by expansion in canals. So in canals, seepage levels will be more. In the case of dams also, the main damage is formation of cracks because of swelling and shrinkage of the soil mass. So cracks are formed. These cracks causes the movement of water from upstream side to downstream side, and in severe condition, it may collapse the dam of the collapse the hydraulic structure. So damages to utilities like water supply and sewer lines. So generally, water supply lines and sewers are laid at a gradient, but because of this expansive soil, the gradient may be destroyed. That's why it may cause damages to water supply and sewer pipelines. Damages in buildings. The swelling soils causes vertical, horizontal, diagonal cracks over the windows and door openings. The floor slab is lifted upwards, leading to cracking of the floor. The footing walls are pushed outwards, leading to breaking of the wall. You can see the cracks in the buildings, so particularly in the openings of the buildings. 1 minute. So because of this expansive soil, cracks are formed. These cracks are found over openings like doors and windows and ventilators. So it may be vertical cracks or horizontal cracks or diagonal cracks. The heaving and cracking of floor slabs, you can see the damages caused by expansive expansive soil to floorings. Then due to excelling nature of the soil, the roof slab are pushed upwards and also walls are also pushed outwards. So these are the damage caused by expansion in the case of buildings. So sometimes expansion also causes tilting of structures. This is because of uneven heaving. So identification of expansive soil. So expansive soils can be identified in the following two ways. One is field observation. Second one is laboratory tests. So I am dealing with the first one, field observations. So in the field, we can identify the expansive soil because spacing and width of wide or deep shrinkage cracks. This is the identification of expansive soil. If the site consists of hexagonal cracks, the spacing and width of wide or deep shrinkage cracks. So it indicates the soil is a expansive soil. So high dry strength and low wet strength. So when the soil is in high dry condition, it is look like a rock. When water is received, it becomes very soft. So this nature indicates the soil is a expansive soil. Highly plasticity of soil. So we can make the soil into our any shape, and also it is highly sticky in nature. So such type of soils indicates it is a expansive soil. Next, shear surface of glazy or shiny appearance. The failure surfaces may be shining. So that's why it indicates the expansive soil. Next, geology and undulating topography. So geology, that means if the water is stagnated at any place, it indicates it is a expansive soil. The evidence of low permeability. So the least permeable soil known as expansive soil. Because of low permeability, the water cannot penetrate through the soil and it stagnates in such type of places. So it indicates it is a expansive soil. So evidence by surface drainage and infiltration features also indicates that it is expansive soil or not. The environmental condition. That means if the cotton is growing uh, very cotton is there's a, if the soil is favorable for growing cotton, it is then it indicates the soil is a expansive soil. At the same time, expansive soils are mostly found in arid and semi-arid regions. So the temperature of the site is more, so definitely if the expansive soil will be formed. The next thing is a laboratory test. In laboratory test, we have some sophisticated equipment and also some simple tests. So the costly equipment consists of differential thermal analysis, X-ray diffraction method, electron microscopy. Next, a simple laboratory consists of freeze-well index, differential freeze-well index, plasticity index, shrinkage limit, and colloidal content. So in differential thermal analysis, there will be a oven. So in first oven, the differential thermal analysis, it is based on fact that certain statistic reaction takes place at specific temperature for different clay minerals when they are subjected to heat. A specific soil with unknown clay mineral is heated continuously along with the inner substance in electron oven, and recorded loss of heat or gain of heat is plotted against the temperature. So here inner substance is nickel. It does not gain or it does not lost the heat, but the soil it is with the unknown clay mineral, it may absorb the heat or it may absorb the heat or it may lose the heat. So these characteristics, absorption and loss in heat, indicate the type of clay mineral present in the soil mass. So by comparing this graph with available records of several known clay minerals, it is possible not only identify the type of clay mineral that present in the given soil, It is also possible to know the approximate quantity of mineral present in the soil by using differential thermal analysis. Here you can see that at 0, it is indicates the nickel substance, this inert material. It does not absorb the heat or lose the heat. But unknown clay mineral, it may lose the heat, it may gain the heat. If it gains the heat, it is exothermic reaction. If it is lost the heat, it is an endothermic reaction. The second one is X-ray diffraction method. The different clay minerals will have different X-ray diffraction pattern based on its crystalline structures. The X-rays are allowed in a specified manner on a given sample of soil, and diffraction of pattern of X-rays are obtained by comparing with standard graphs. So the unknown clay minerals is identified, and also it is possible to know the amount of clay mineral present in the soil's sample. So here X-rays are allowed to fall on the soil sample containing unknown clay mineral. So after falling on the soil sample, depending upon the type of sample, it may refracted, it may be diffracted. So the diffraction angle depends upon type of clay mineral present in the soil mass. So different clay minerals will have different diffracted angles. So by comparing this one with the standard graphs, we can identify which type of clay mineral is present in the clay and also how much amount of clay mineral is present in the clay. Electron microscope. So in this method, the soil sample is observed under polarized light in the electron microscope. So texture and certain characteristic stains are indications of type of clay mineral present in the soil sample. So by using electron microscope, we will observe the texture of the soil mass and also certain characteristic stains of the clay soils. So these texture and characteristic stains are different for different type of clay minerals. So by comparing these standard clay minerals, we will identify which type of clay mineral is present in the soil sample. So electron microscopy, differential thermal analysis, and X-ray diffraction. These are costly equipment and also need a skilled supervision. So apart from this, we can also have some simple laboratory tests which can be used for identification of expansion size. They are pre-swell index (FSI). It is called as pre-swell index. In this method, a 100 cc jar is taken, 10 grams soil passing through, 425 micron is poured into the jar. The jar is filled with water. After 10 minutes, the height of the soil in the jar is noted. So after 24 hours, the height of the soil in the jar is again recorded. Then free soil index is expressed as volume of soil in water after 24 hours minus volume of soil in water after 10 minutes divided by volume of soil in water after 10 minutes into 100. If free soil index is less than 50%, no problem for lightly loaded loading lightly loss. If free cell index is greater than 100%, it causes considerable volume changes. So type of clay mineral and free cell index. So if free cell index in between 1200 to 2000%, so then it indicates amount of clay mineral is present in the soil sample. If free cell index is 80%, it indicates the type of clay mineral is kaolin. If the free cell index in between 30 to 80%, it indicates that type of clay mineral present in the clay soil is illite. The next simple method is conducted in laboratory is differential free soil index (DFSI). So in this method, two samples of overwanted soil weighing 10 grams each passing through 425 micron series are taken. 10 grams is put into a 100 ml graduated glass cylinder containing water, and another 10 grams put into a 100 ml graduated glass cylinder containing kerosene. So both the samples are left undisturbed for 24 hours. Then readings are noted. So DFSI is expressed as DFSA equal to volume of soil in water after 24 hours minus volume of soil in kerosene after 24 hours divided by volume of soil in kerosene after 24 hours into 100. Here, kerosene is used as a reference because kerosene is a non-polar liquid. It does not have any interaction with the negative charge of the soil. So clay surface consists of negative charge. It always attracts the positive charged cations or positive charged water molecules. But kerosene is electrically neutral. It does not have any interaction with the cations or water molecules. That's why kerosene is taken as a reference one. With that one, we will compare the volume of soil in water that is taken place. The classification of expansive soil based on DFSA. 1 minute. If DFSA is less than 20%, degree of expansion is low. So the soil is treated as a low degree of expansiveness. If DFSA is in between 20 to 35%, the soil is treated as a moderately expansive soil. If DFSS is in between 35 to 50%, the soil is treated as a highly expansive in nature. If DFSS is greater than 50%, the soil is treated as a very high degree of expansiveness. So next simple test conducted in laboratory is plasticity index. So the numerical difference between liquid limit and plastic limit is called the plasticity index. The classification of expansive soil based on plasticity index. If plasticity index is in between 0 to 15, it is called as a low swelling, a low degree of swelling, a low degree of expansiveness. If plasticity index is in between 10 to 35, the swelling potential is medium. If the plasticity index is in between 20 to 55, eh, the soil it has a high degree of expansiveness. If plasticity index is greater than 55, then the soil is treated as a very high. Swelling potential of soil is very high. So another simple test conducted in the laboratory is shrinkage limit. So the water content at which the soil changes from plastic state to semi-solid state is known as shrinkage limit, or the water content at which the drying of water does not cause any change in volume of soil is called as shrinkage limit. At shrinkage limit, water is still saturated condition. The classification of expansive soil based on shrinkage limit. If shrinkage limit is less than 10%, the linear shrinkage is greater than 8 and the degree of expansion is critical. So the shrinkage limit is in between 10 to 15. The soil is called as marginal or medium degree of expansiveness. If shrinkage limit is greater than 12%, the degree of expansion is low, very low. So it is called as a non-critical. Next one is shrinkage index. So shrinkage index also used to identify whether the soil is expansive soil or non-expansive soil. The shrinkage index means the numerical difference between plastic limit and shrinkage limit is known as shrinkage index. The classification of expansive soil based on shrinkage index. If the shrinkage index is in between 0 to 20%, the degree of expansiveness is low. If shrinkage limit ranges in between 20 to 30%, the degree of expansiveness is medium. If the shrinkage index is ranges in between 30 to 60%, the degree of expansiveness is high. If shrinkage index is greater than 60%, the degree of expansiveness is very high. Next, classification of soil based on colloidal content. The particle size having less than 2 microns, then the soil is called as colloid. So if the colloid presence of colloid percentage is less than 15%, the degree of expansion is. So if the colloid percentage less than 15%, the degree of expansion is low. If the colloid content is in between 13 to 23%, the degree of expansion is treated as a medium. If colloidal content is in between 20 to 31, the degree of expansion is treated as a high. If colloidal content is greater than 28%, the degree of expansion is very high. Next one is a swelling potential. The swelling based on swelling potential also, we can use this parameter to classify the expansive soil. So swelling potential is the maximum capacity of soil sample to swell under a pressure of 6.9 kN per meter square placed over a soil sample which is compared to OMC and MDD in the standard Proctor type. So first we need to prepare a soil sample at OMC and maximum density by using standard Proctor test. Then 6.9 kilo per meter square surcharge is placed over the soil sample. Then the soil is allowed to swell. So at this condition, the maximum capacity of soil sample to swell under a pressure of 6.9 kilo per meter square is known as swelling potential. The swelling potential depends upon percentage of clay material and also activity of the soil mass. The swelling potential is equal to 3.6 into 10 power minus 5 into activity power of 2.44 into percentage of clay whole power 3.44. So whereas C is known as percentage of clay, that means the particles are less than 2 microns. The activity of clay equal to plasticity index divided by percentage of clay fraction. The swelling potential also expressed in terms of plasticity index. So it is directly proportional to plasticity index. More the plasticity index, more will be the swelling potential. So swelling potential equal to 2.16 into 10 power minus 3 into plasticity index whole power 2.44. So swelling potential equal to, so swelling potential also expressed in terms of shrinkage index. The swelling potential equal to 41.13 into 10 power minus 4 into swelling in shrinkage index whole power 2.67. Classification of exponential based on swelling potential. The swelling potential is in between 0 to 1.5. Degree of expansiveness is low. The swelling potential is in between 1.5 to 5. Degree of expansiveness is medium. The swelling potential is 5 to 25%. The degree of expansiveness is high. If the swelling potential is greater than 25, the degree of expansiveness is very high. Swelling pressure. When a sponge soil receives water from outside, increase in volume of soil takes place. So the increase in volume of soil exerts an upward pressure onto the structure resisting on the expansive soil. So the upward pressure exerted by the expansive soil is known as swelling pressure. So when expansive soil receives water, swelling of soil takes place. This increase in volume of soil mass exerts pressure on the structure which is constructed over the expansive soil. So the upward pressure exerted by the expansive soil is known as swelling pressure. The swelling pressure also defined as the maximum force per unit area that needs to be placed over a swelling soil to prevent the volume increase. Suppose so a soil is taken, uh, a soil is sample is made at OMS and MDT, then it is allowed to swell to its maximum capacity. Then a force is applied over the swelling soil to attain its initial volume. The maximum force per unit area that needs to be placed over a swelling soil is to prevent volume increase is known as swelling pressure. Swelling pressure is determined from the following three methods. They are free swell method, constant volume method, different surcharges method. In free swell method, the soil sample is prepared at its optimum moisture content and maximum density. The soil sample is placed in water and it is allowed to swell freely. After reaching maximum value of swelling, then the specimen is compressed to reach its initial height or volume. So the maximum force applied per unit area over a swelling soil to get its initial volume is the swelling pressure of the soil mass. So in free swell method, the soil sample is prepared to OMC and MDD. The soil sample is placed in water and it is allowed to swell freely after reaching maximum value of swelling. Then the specimen is compressed to reach its initial height or volume. The maximum force applied per unit area over the swelling soil to get its initial volume gives the swelling pressure of the soil mass. The next one is a constant volume method. In this method, the swelling pressure is measured for a no volume change condition. So the method requires a continuous adjustment of pressure and soil specimen taken in consolidation cell so that the soil volume at any time equal to its initial volume. So the name itself indicates that it is a constant volume method. So at any stage of the experiment, the volume of the soil sample is constant. So when it receives water, swelling of soil takes place, but by continuous adjustment of this adjustment of proving ring, the volume of the soil kept constant. That's what is called as constant volume method. Next, different surcharges method. In this method, four suitable number of identical soil specimens are prepared and they are subjected to different magnitude of surcharge pressures, and these soil samples are allowed to saturate at different surcharge intensities. Some soil specimens would compress while some other would swell. So that means four soil samples are prepared at same optimum moisture content and maximum density. So two soil samples are subjected to low pressures and two soil samples are subjected to high pressure. So after recording volume changes under pressures, a graph is drawn between volume change and surcharge pressure. So from the graph, the swelling pressure corresponding to zero volume change will give the swelling pressure of the soil mass. It is much more convenient to plot load intensities on logarithmic scales as a curve producing a straight line. So the percentage change in sample height is indicated on y-axis. The applied stress is indicated on x-axis. So here the zero, the percentage change in sample height is zero. So here the line connects the zero pressure line. So where the line uh, cuts the zero pressure line, it indicates the corresponding applied stress indicates the swelling pressure of the soil mass. The field conditions that favor swelling. So sometimes the swelling will be more and sometimes the swelling will be less. So this swelling depends upon the following factors such as initial density, initial moisture content, type and amount of clay mineral, method of compaction, stress history, height of soil sample, time of contact with water. Surcharge. If all the parameters remain constant, the surcharge pressure increases over the expansive soil, the swelling pressure of the soil decreases. Hence, it is recommended construction of multi-stored buildings on in expansive soils. In expansive soils, it is recommended that to go for multi-stored buildings so that the downward pressure will be increases. When this downward pressure is more than the upward swelling pressure, then no problem in the expansive soil. That's why. So for lightly loaded structures, it causes severe damages. That's why we will recommend the multi-story buildings in the case of expansive soil. The initial density. So if all other parameters remains constant, the density of soil increases, the swelling of the soil also increases because density is more. It accommodates more clay minerals in the soil mass. That's why swelling of soil mass also increases. Next, initial moisture content. If all the other parameters remains constant, if initial moisture content of the soil is less, there will be more swelling of soil mass or vice versa. So if all the parameters remains constant, that means the surcharge, initial density, and another other parameters remains constant. If initial moisture content is less, there will be more swelling because thirsty of water. If initial moisture content is more, there is no thirsty of water. That's why it does not imbibe the water. The swelling will be reduces. Type of an amount of clay mineral. The soil containing more component clay mineral tends to expand more when compared to other clay minerals. As the amount of clay mineral increases, swelling pressure also increases. So as the type of clay mineral is present is a more clay mineral, swelling will be more. If the amount of clay mineral is also more, then the expansion of soil also increases. Then one is method of compaction. So in the case of expansive soil, the soil is recommended to compact and wet side optimum because presence of more moisture content and a less density. So, if the moisture content is more, thirsty will be more, so that swelling pressure will be decreases. If the density is less, swelling pressure also decreases. That's why in method of compaction, it is not recommended to compact the soil at optimum moisture content. It is recommended to compact the soil on wet side of optimum moisture content because of presence of more moisture content and less density. Test history. The over-concentrated soil have a tendency to swell more access to water when compared with normally concentrated soil. So over-concentrated soil have more densities compared to normally concentrated soil. So over-concentrated means the soil which is subjected to more stress in past. So they will have more density. So as they have more density, the swelling nature soil also will be more when compared to normally concentrated soil. Height of soil sample. With the height of soil sample, thickness of soil sample is more, the swelling pressure of soil is also more. The height of soil sample or thickness of soil sample increases, the swelling nature of the soil increases. The swelling of the soil also increases. Next, time of contact with water. The time of contact with water soil increases, the more contact with water soil is available, so that swelling of soil also increases. If the contact time with the in between water and soil is less, then less swelling will be taken place. So this is about briefly about expansion soil. In tomorrow's class, I am going to explain. So what are the preventive measures to be taken in the case of expansion soil? You know, Pranay,
Sir. Sir.
tomorrow I will explain the remaining things.
Okay, sir. Thank you, sir.
Okay, okay, Pranay, thank you.
Okay, sir. Thank you, sir.